Yeah, so welcome everyone to the Formal Methods for Software Engineering lecture. Is this your first lecture here? Well, some of you I know it's not, but for who is it the first lecture? Okay, great. Yeah, nice to have you here, and nice to have everybody else here, of course. Yeah, so which semesters are you in? I guess, well, if it's the first one, then you're in the first semester, right? Who's in second? Okay, who's in third? Who's in fourth? Should I stop asking now, or? Okay, I mean, yeah, everybody has their reasons, but yeah, great. Okay, so yeah, this one is the Formal Methods for Software Engineering. And if you are in computer science for digital media, I think you can put it in the, what is this block called? Data science, right? Yeah, so you can use it there. If you are in digital engineering and you started this semester, then you can use it also in the computer science methods. If you are in digital engineering and you started earlier, it will not automatically be available to you in the block called Visualization and Data Science. But if you request in the examination office that they allow you to take this for that block, then they will simply send it to the head of the examination committee and they will approve it because it is already approved for the new intake. So it's just not updated for the old study regulations, which is always a bit tricky because everybody who started in a specific study regulations, they keep their study regulations until they finish, right? So if you want to, you can always take it as an elective. This works for, well, every program, I guess, at this university. But if you are in, if you need it in a specific block, just check if it's not listed on Bison, it might still be possible. So just, yeah, check with the examination office. And usually it works, but it doesn't work automatically because based on the study regulations, they have to assign it as elective. But if you ask for it to be moved, then they will do that. Okay. Yeah. So, well, this is me. I'm a professor of software who had a lecture with me before. Oh, okay, great. Why don't you raise your hand? Ah, you did. Okay. Okay, great. Yeah, so some of you know me. My research interests are in model-based software engineering, well, software engineering in general, but then also automotive and autonomous vehicles, software synthesis for robotic systems, and also software verification. And this is where Formal Methods also plays a big role. And the teaching assistant, you might also know that's Shoaib. He did his master's in automotive software engineering, but he's now also doing in his PhD. He's also working on more formal methods so far. So he's here for 1 year now. Yeah, and the teaching will be like this. We usually have lectures and tutorials. There's some difference between the lectures and the tutorials. So the lectures, they will be with the presentation of new materials. Like we will do, well, today it's more like an introduction, but then as soon as we are done with the introduction and setting the expectations, we will start with new materials, learning new stuff. And this will be mainly me talking to you and you, I don't know, taking notes or reflecting or something. And then we have the tutorials, which are somewhat more led by yourself. So we will, there will of course be either Shoaib or me or both of us here, and we will show you what is the current task. And then we expect you to work on this task. So in many cases, to work on this task, you will probably need a computer. The idea is that you can work on these tasks in 2 people, so this makes a lot of sense. In particular, when we are all sitting here together, you can ask us questions while you start solving the tasks, and you can ask your partner questions while you start solving the task together. So for all these things marked with E for exercise, or, well, yeah, they're marked with E for exercise in Moodle. For all these, it would be a good idea to bring a computer. A phone might also work, but yeah, computer might be helpful at some point. Yeah, it won't work for all the exercises. And then, of course, there might be questions and hopefully answers. So one way we can do this is, of course, here after class or in class, just as soon as some question pops up that you think is relevant, right now, then just ask it. Just raise your hand and ask it. Otherwise, if something pops up while you're at home trying to work on the assignments, then please post it in the discussion forum on Moodle. There are, of course, some rules about preventing collusion and plagiarism. So if you're working on something that is some kind of unique solution to a homework and you have a specific question, it's always good to post as much information as possible. But it's not good to post your solution so that others can simply copy your solution. We had a case last semester when we were teaching this for the very first time. So we used GitHub, and we put some of the programming stuff on GitHub so that people could then fork the repository or create. I think we had it as forks because it was not a template project. So basically they could fork it, and then because it was a public repository, they couldn't make it private. And then you can just check who forked this project. And right before the submission, somebody who forked the project probably was done with the project, and you could copy their code. You shouldn't do that because that is plagiarism, right? I think we will maybe change this slightly. So on GitHub, you have this option to do a template project. And then I think if you create a project from template, you can make it private. You can later, of course, make it public to show your work to the world. But maybe before the submission, be careful to not share your solutions with others. Okay, but I think that's self-explanatory. So if you post something in the forum, the benefit is that everybody will see the answer, and maybe you have a burning question at, I don't know, Tuesday night or something, then post it there. We might already answer it on Wednesday morning before the next session even is on Friday. So, and if you see that some other people have questions in the forum, please, feel free to answer to them, right? It can be some discussion, or if you have a different aspect of that question, just post it there, and then we try to answer it, or you try to answer it. So this, if it works, it usually works quite well. That's about the question answers. Have you checked the Moodle page? So let me just. So no, that's the one from last. Okay, so here would be this question answer forum. It is configured to be, I think there's like a message tracking thing, and it's configured to be automatic subscribed. So everybody is automatically subscribed here. So if you post a message, everybody will get an email. If you get too many emails, you can go to the configuration of this forum and just unsubscribe. So you can say you don't want to track this forum, because I've heard from some students that they don't get important emails because they get too many emails from, let's say, forums. So because I'm not expecting a lot of traffic on this forum, I thought I'll do automatic subscribe so that if there's a question, everybody will see it. But you have the option to simply turn it off and then not get those emails. And it's probably a good idea to turn it off here in Moodle, better than setting up some filtering rules in your email, which might catch other important stuff, and then you don't see it. So this is the, I don't know why this new, so this thing is new. Okay, great. Okay, so that's an overview of the sessions. You will see that many of them are with an L, and some of them are the ones with an E. So the ones with an E are those kind of exercises where there won't be a lot new material. Sometimes if we don't manage to present all the material in the session before, we might take, I don't know, half an hour of the exercise to finish delivering the lecture parts and then move to the exercise. But in general, you should expect that if it says here this exercise, then it will be more like you guys sitting in pairs or alone on computers, and Shoaib and me just being here to answer your questions and help you set things up. Okay, and there are, of course, some meetings that can't take place because of holidays. yeah, and university closures. But usually, if you look at these this schedule, if you look far down here, this might not be the actual order of the sessions. This is just what we have planned, but things might change slightly. So you can expect that the current and the next one are kind of up to date, right? So today is this one, and yeah, that's up to date. So the one of the upcoming one is always the one up to date, but the other ones more in the future, they might change a little bit, might be adjusted. So if you, I don't know, look at this and say, oh, that day it's alloy modeling hands-on, I might take a vacation or a day off, then it could be that actually it will be only introduction to relational first-order logic, and you'll miss that. So yeah, don't plan too much ahead with based on this schedule because it might change. I will usually link the lecture slides here before the meeting so that in the morning when the lecture starts, you can download the PDF if you need to annotate it or read along. Then this should all be available. Sometimes it's really just available in the morning of the lecture. Okay. Any questions about this Moodle? Okay. Yeah. Then, yeah, how are we going to assess this module? Anybody knows how this will be assessed? Will there be an exam? Will there be a project? So this will be a project. I think it says in the module handbook, so we can't really very easily change this. We will assess this with a project. So what will happen is that there's probably a slide about this, that in the end of the teaching, so probably before the Christmas break, we're going to give out project topics. And then in your group, you pick one of those topics. There will be some kind of, selection round for the topics. You will check which ones do you prefer the most. And we will only do it then because then you have learned most of the materials that will actually allow you to judge whether this topic is a good topic for your project. And then you'll do this kind of mini project, and it will be probably the submission is due sometime after the examination period. And then we will show you how we're going to mark it. There'll be some certain elements and weights about maybe some intermediate presentation, some final presentation, the technical achievements, stuff like this. This will be on some of the later slides where we're going to introduce the projects. But yeah, you work in small groups. Usually it's 2 people. 3 might be a bit too much. 1 person might also work if there's really no other way, or if you're in a group of 2 and then somebody leaves, then also 1 person works. So we last year we basically did the majority was groups of 2, and then there were some groups of 1. Yeah. So to participate in the assessment, this is very common that you have to do the exercises to then be qualified to participate in the exam or in the project submission. So that's also what we're going to do here. Whenever you see these things with E on Moodle, we usually release some tasks. And there are some tasks which you have to submit within 1 week, and some which you have to submit within 2 weeks. So there are kind of 2 different kinds of tasks. One where it's mainly using some tool, and then we give you 1 week, and then one where you have to do some coding yourself, and then you have 2 weeks. Yeah. So you have to submit those and present the group submissions during the tutorial. So if we have some questions, you need to be able to answer. So this is not a formal presentation. It's just if we ask you about this, you have to show us the code and tell us how you did it, right? So there's not a presentation where you have to stand here with slides for these for this kind of homework assignments. But there will be, for the project, we're expecting some kind of intermediate presentation with slides to everyone so that everybody can see what are the other guys doing and where are we in terms of how is our project going to be, and we give some feedback then. But that's, in next year, basically. Next calendar year. Yeah. Okay. So, you need to pass all of these assignments. So this will be something like, yeah, I'm not sure. Maybe could be 7 or 8 assignments. And you can submit or resubmit 2 of these assignments. So let's say you're doing very well in the beginning, you pass all the assignments easily, and then later you fail an assignment. We will tell you, okay, you have the chance to resubmit this assignment, and then you can resubmit this assignment, so you can still pass and then still be admitted to the assessment with the project. So yeah, ideally try to submit it by the deadline and try to submit it good enough to pass. And it's just a pass or fail. There's no very, very well elaborate marking. We will just check would this be qualified as a pass or as a fail. So if you make very small mistakes, then probably we will just say, yeah, it's still a pass, because the hassle of you going back into your code, fixing those things, and then us reviewing it again, maybe that's too much. But if there are larger problems, then we will ask you to resubmit. Okay. Yeah. Any questions about this organizational stuff? So there'll be more information on this as we go. So particularly about the assignments, we will give you worksheets, and then for each worksheet, you will see what exactly are you expected to submit. Okay, so yeah, now let's start with an introduction to the topic, so that you not only know how we're going to do this, but also what we're going to do, right? Yeah, so we will do this a little bit interactively. So I should have set this up earlier. Okay. Okay, so if you have something with an internet connection and a browser on it, it would be great if you could type in this URL, Particify, well, 6271. Everybody can read it? So this URL is also on the slides. So if you have the PDF version of the slide, you can simply click on the link. And this URL will be the same URL for all of these kind of question answers during the lectures. So if you have typed it once, you can maybe bookmark it. And then every time I put up another question, you might just have to refresh this thing and not type up the URL again. So the numbers, they don't change. I just select what you're seeing and where you can answer. Okay, so the first question would be, what is formal methods? Some of you might have an idea. Some of you might have Googled it before you decided to come here. If not, just put a wild guess. So this one, this Particify, this is hosted in Germany according to all the data protection rules. So it's completely anonymous. You don't have to sign up for an account. I think you can sign up for an account, but yeah, and it's all. So I've seen multiple universities use this. There are some systems which other people use, which are maybe not completely conforming to the German data protection rules or laws, but this one does. So you're on the safe side. And I won't use it for any marking. So if somebody puts a really, yeah, there are no stupid answers, right? No stupid questions. Are there stupid answers? I don't know, maybe. But yeah, it won't affect your marks. And if you really have no clue, or if there are any misconceptions, it's good to put this stuff here so that we can clear them up, right? It's bad to, I don't know, wait until next year examination period and realize, oh, formal methods is really not what I expected, right? So that's why we're trying to check. Yeah, so okay. Yeah, so let's see. We have some answers here, right? Mathematical methods used for software design. Very good. So why Who wants to explain this? Anybody wants to explain this? Okay, so it hits some very good points. So it says software design, right? We have this software, it doesn't write itself. We have to design it. We have to make sure that we build the right software and that we build it in the right way. And then mathematical methods. So yes, there is some math involved. The formal methods, that's basically often that's the mathematical part. Then designing software in a universally understandable way without actually coding it out. Yes, so you don't necessarily have to write all the code to apply formal methods. There are some formal methods which actually do work on code, but many of them, they work on more high-level designs and abstractions of the systems, and then they allow you to already, maybe understand and analyze the system that you're going to develop, and then without actually coding it. So yeah, I said some methods, they actually work on code, some work on design, and some formal methods, they actually write the code for you. So that also exists. Then mathematical model to create or solve the software hardware. Yeah, so that's maybe a bit similar to the first one. But yeah, it's not just a model, it's really a method. There might be multiple models involved. So there might be different models of computation. So when you're looking at concurrency, then you have different maybe models of concurrency, different models of memory access in systems. So all of these might be different models, and then there are methods that you can work with these models. And then here, that's very good. So formal methods are not limited to software. They can also be applied to hardware, and we will maybe see some examples of where they are actually applied to hardware as well. Okay, yeah, that was good. So here is some definition. Formal methods refer to mathematically rigorous techniques and tools for the specification, design, and verification of software and hardware systems. So here, based on this definition, we see, yes, it has hardware and software. But of course, we don't always have to have the two. We could just focus on the software. We could just focus on the hardware. If we focus on the interplay, it gets really complicated, but also that exists, of course. So if you want to analyze some, maybe some real-time Linux kernel for some really important system, then you have to look at the interplay between hardware and software usually, and that makes things much more complicated. But people have done this and are doing this. So then, we have these mathematically rigorous techniques. So we have techniques and tools. This is also important. It's not just techniques that we have to apply with pen and paper. It's also supported by tools. And from a software engineering perspective, the tools part is really important because this is what allows us to scale to some extent, right? We can automate parts that otherwise we would have to do by hand. And we will actually, in this lecture, we will look at kind of how mathematically something can be formalized. And then in each section, we will first look at what's the, let's say, theory background. And then we will look at what are the tools that will allow us to use this and apply this. So for us, for this lecture, because we want to apply it to software engineering, tools are really important. And we will look at, I think, 4 different tools throughout this whole lecture. And they all have, some different capabilities. Yeah, then design verification of software. So some, they help you to basically create and analyze the software, and some they help you to verify to make sure that it works as intended. So if you have a design of the software and the actual software implementation, then the verification will tell you whether your implementation really satisfies your design. Okay. So the ingredients are this mathematics that we see in there. For computer science, it's a lot based on logic. But we don't only need the logics. We usually also need languages to express things in this logic, right? So many of you know maybe the Boolean or propositional logic, where you have variables, ABC, and then you have some operators to connect them to actually build some sentences. So the languages are always the important ingredient. If the language is maybe too complicated, or if the language doesn't allow you to express the problem that you have, then you can probably forget about this particular method because you can't really apply it, or it's very, very complicated to apply it. So the languages are quite important, and the languages, that's basically maybe similar to programming languages, but we will see that, yeah, so in terms of which language is suited for which problem, I think you can easily compare it to programming languages. Some programming languages are very good for maybe machine learning. Others might be very good for web front ends, stuff like that. And we will also have this within the languages that are in formal methods. Then, of course, the tools. There are some people that don't like tools and they want to do everything by hand, but I think most of us, we appreciate that tools can automate things and do some analysis for us. This would be, that would maybe be a bit more complicated by hand. And then, of course, there needs to be some purpose. So we shouldn't forget this. The formal methods, they don't just exist because somebody really likes logics, languages, and tools. There must also be some purpose. Why do we want to apply this formal method? What problem do we actually want to solve? And for these purposes, what we will do in each of those chapters that we have, so those 4 main tools and logics and languages that we will look at, we will also look at what are typically things that people do with these tools. What do they analyze? What kind of systems do they ensure to work correctly? So that's also something. Basically, for all of these 4 chapters, we will have this structure. So we will look at what's the logic behind it, what's the language that we can use to express the problems, what are the tools, what can the tools do for us, and then what do other people use it for in practice. Okay, yeah. So now the why, this kind of purpose. Why do we actually need this? Well, logic is maybe just another language, or there are some languages just based on logic. Why not use English or Java, right? Most of us, we know these 2 languages, and well, we also know logic, but maybe we're more familiar with English, right? All these languages, they basically have some words, some rules to combine these words to make sentences, and that's basically the syntax. So I might write down some combination of letters or words that don't make sense, but they still are written in, I don't know, Java or in English, right? They might not compile. So for something to compile or to make sense, we need to look at what's the meaning of these words and sentences, and that's called then the semantics. So in this machine learning area, people are also looking a lot at extracting semantics from the English language or other languages to see what do people actually mean by this. They just don't want to just check, okay, that's a sentence, and this sentence might make sense because nothing is misspelled. You're trying to actually understand what's going on there, and what is the, let's say, the semantics of Java? Or who would need the semantics of Java? Do we need this, or do we just need to write syntactically well-formed programs? So syntactically well-formed, this might mean that if I have an opening curly bracket, I need a closing one, right? That's some kind of syntax rules. Okay, why do we need semantics? Why do we need to know what's the meaning of these words? Why do we need to know the meaning of system out print line? Yeah, what actually it does. So if we don't have a semantics of it, it could do anything. We know that system out print line prints something to the console, right? So the semantics is really important. And what gives the semantics of Java or programming language? Often we have some tool called a compiler or an interpreter, and they actually give the semantics of the language, hopefully correctly. There are some works that say that maybe the compiler doesn't really give the correct semantics. So they mathematically define the semantics, let's say, of C programs, and then they can check C compilers whether they really implement this semantics. And that's how people often find bugs in compilers. Okay, but yeah, why would we need to learn another language? Is there stuff? Yeah, what's the problem with English and Java?
if we try to just generalize to design like a procedure, a system that we understandable for more people for specific.
Okay, so we want it to be understandable for more people. What do we need for this to work? What are the challenges with English? I mean, you probably have more people that understand English than logic.
Explain the system in English, it's too much explanation.
Okay. Yeah, it might be quite verbose, but there might be also some issues with if we say something, we have a specific meaning in mind, but maybe that's not the meaning that the person who hears it actually receives. So if we say turn right here, right? This could mean I'm here and I need to turn right. Or it could mean right here, I need to turn. So I don't know, whichever way, right? So there's some ambiguity here. Turn right here means either right at this spot I have to turn, or I actually have to turn in the right. Well, yeah. Let's let's not get more ambiguities. Yeah, he saw her duck. So either she has a pet duck, right? Or she actually ducked down because something was flying over her head, right? Yeah, visiting relatives can be fun. Now, here, what are the different meanings?
Who's visiting who?
Yeah, who's visiting who? Are the visiting relatives coming to you, or are you the one visiting relatives? Might be very different. Yeah. Okay. Yeah. So there is some imprecision, some ambiguity in natural language. That's also what. Well, if you heard the software engineering lecture, we talk about this precision, ambiguity in English, and we look at all kinds of things that we need to do, maybe to write down requirements, because the most common languages for software requirements, that's English, right? In your specifications, you often write English language. And then we have all these issues of ambiguities and imprecision. Okay, why not use Java? That shouldn't be ambiguous, right? Because there's some compiler that does exactly what we write down, hopefully. So what does this one do? Well, it returns some Boolean, right? So it makes a decision whether something is true or not. Here it says it's not true. And in all the other cases, if x greater equals 1, it says it's true. So actually here it multiplies two things. And if they give the input, it says it's false. So what do we know about this input now? So we can check whether the input is a prime number, right? Because if we multiply two numbers and we get the input, then it's not a prime number because it's divided by R, Q, and maybe more, right? Because R and Q might not be prime numbers. So yeah, all this code just to say we're looking for a prime number. Maybe Java is too verbose here. Also, in Java, we usually have to express how do we actually check that something is a prime number. We have to say, yeah, we iterate over factors starting from 2, and then another factor starting from 2, and then we try to multiply them. So there are many operations going on here, and all we want to say is that this number basically, is a prime number, that it's not divided by any other factors other than 1 in itself, right? So that's a bit verbose. Now, why do we use logic? We want to express a system and an environment behavior with the logic. So an interesting thing is that usually when we write code, we often think only about the behavior of the system, because that's what we're coding, right? We are implementing how the system should behave. But in many cases, the system is not standalone in thin air. There's stuff around the system. If we program some robot, this robot will recognize stuff from its environment. and the environment might behave differently to actions that the robot does. Or if we're using some API, then maybe the state of the environment changes based on the API calls we do. So we usually want to express both the system and the environment in logic. So then we would express the expected properties that the system should meet, and we would now need another language, or maybe the same language, to express these properties. So we say we want to learn something about our system, or we want to assert something about our system, and then we can use tools to check that really our system behaves like that. And if we formulate all of this in logic, then it's quite easy for us to check this. So does this remind you maybe about software testing? What's the difference with software testing? You write some system or part of a system, right? So that's, here, but maybe in a programming language. Then the expected properties. What's that in software testing? That's your test cases, right? So that's the test cases you write. And then you check that only valid behaviors occur. That's, well, executing the test cases on the code that you've written, right? So what's the difference? Why not simply use testing? So the problem is that, well, there's this quote by Dijkstra that testing can only show that bugs exist, but it can never show the absence of bugs, right? Because usually we can't test exhaustively. So if we find a bug, we know there is one. If we don't find a bug with testing, there might still be one. We just haven't found the right input to produce this faulty behavior, right? So yeah, we can gain confidence in the correctness of the code, of course. If we have 10 test cases and none of them fail, and they are of good quality, then hopefully our code is correct. But we don't really know because we can't really test everything, every input. And also, it's very difficult to deal with non-deterministic programs. Did anybody ever write a non-deterministic program? So there are some research areas where they focus on this non-determinism and probabilistic programs. So you can then reason about executions where you have some probabilities in the program that something happens or that something else happens. And in some fields, there are some very efficient randomized algorithms. They're not often deterministic, but we might still want to prove something about them. So with test cases, if our program has possibly different behaviors for the same input. So this non-determinism means that, or deterministic programs usually mean that for the same input, we get the same output. And most of the time, if we don't use any random numbers or any external calls, let's say we call a sorting algorithm on a list, and we call it on the same list, and it's some implementation like quicksort or bubble sort, we would get the same output, right? But if the program is non-deterministic, it might give us different outputs. And if we even have non-deterministic programs, how often should we run every single test case to observe all the different non-deterministic behaviors? So yeah, it's kind of hopeless, but with formal methods, we actually have ways to address this non-determinism. So we will see, well, some ways to put in non-determinism in our programs, multiple possible solutions, and we can check all of them in the tools. Of course, with some limitations. So formal methods is not the solution to every problem, but there are some problems where formal methods is the solution. But there are some which we just simply can't solve even with formal methods. Okay, so yeah, if we want to look beyond testing, then we also have some issues that maybe in some graphs, if we want to look for shortest paths, for example, there might be multiple correct solutions. So in testing, we would maybe check, does this find, well, depending on if we want to go from G to E, what's the, well, shortest path? Then it might find this one here, GHFE, or it might find GABE, and they both probably have the same length. They're even weighted here. So this is 11 long, and that one is yeah, also 11 long, right? So we might have multiple possible solutions. If our test case just checks whether this is the shortest path, the test case might fail, right? So that's why maybe we want to go with logic and describe the oracle in a more concise way. So here, the oracle is always the output of the expected output of the test case, right? So now what's the expected output? We could, well, look for all the shortest path and then say any of them is the expected output, but yeah, that gets a bit tricky. So yeah, how would we write this? So if we have multiple correct outputs, then we're really testing a relation. So a single input could be related to multiple correct outputs. Usually in a test, you have a pair of input and output, but here now you suddenly have a relation. It's no longer a single pair, it might be multiple pairs, and you want to check all of them. So it's not really like a one-to-one as we would have in a pair. And some problems face similar difficulties, like the minimum spanning tree. There's usually also multiple correct solutions, sorting algorithms. If you add stuff like identities of objects, then maybe there's also some multiple solutions here. So yeah, we sometimes need to go beyond testing. So if we have some method is valid and it consumes some input and output and determines whether the output is a valid solution of the given input, then how would we write this for the shortest path problem? We would take a graph, which is basically this kind of sequence of vertices that similar to the graph that we just saw, and then we would need to check whether the sequence of vertices actually is a path in the graph, right? We could get a shortest answer, but that's not a path in the graph. I could just simply give you a note that is maybe not related to the graph and say, oh, the shortest path is 1, right? But that's not a good solution. Does the path start with the source and with the destination? Yeah, we would also want to check that, right? And is the path actually the shortest path in the graph? But that's like, yeah, the same as checking the same kind of algorithm. So that's quite tricky, but this is actually this is quite a different formulation, because here what we're formulating are properties, maybe written in some logic, that we could check, and they are not inputs, outputs, like the traditional testing. So the idea is we could test against properties instead of testing against values. And then we suddenly have a lot more opportunities. Yeah, and well, finally, people are usually bad at writing large and complex software systems, but yeah, software is taking over all kinds of aspects of our life, and failures, they have increasing consequences. So I don't know, who has ever written flawless code? Raise your hand, please. No? Yeah, me neither. It's usually has some bugs. So here are some examples of everyday systems that might fail and that might be faulty. So there's some popular examples from the financial trading industry, the Knight Capital Group. They basically had a bug in their system. Yeah, and I think they basically had an automated trading system that they wanted to explore, automate, and then they lost 440 million because this thing didn't trade in a good way, not in a good way for them. Then there are some other examples in games where some kind of viruses were actually accidentally introduced, viruses that would affect the gameplay, or in cars, of course, and in cars it's even maybe more critical than, let's say, in games. Some people might see this differently, but there were some issues with Toyota cars. So the thing is that a car without software basically wouldn't run anymore. So all the cars today, they have millions of lines of code in them. and there are some functions are for convenience. So one thing is the way that you press the accelerator pedal. You want this to feel nice, to feel powerful. So it's actually not like in a normal direct mechanical way that you press it down and the fuel is released based on the angle. That's not how it works. There's some computer calculating what's the best way to make the driver feel based on how they press the pedal. And then there are people that are fine-tuning this. And different companies fine-tune this differently. So Mercedes fine-tunes it differently from a BMW or a Volkswagen. And that's a huge branch of industry. So there are, of course, also some cases where the brake system might not work. I think the problem here was that there were some combination of hardware faults and a software that was not written in really a fault-tolerant way. So maybe some bits were flipped because of some hardware defects, and then suddenly a car would not be able to stop anymore, and the brake system would fail. And maybe even the acceleration would go up. I'm not sure, but this was a really serious issue in Toyota cars with multiple people also dying because of this software issue. And again, software testing. So usually in testing, we can check a few executions of some size based on how much money and resources we have. Then there is something already in formal methods, which is called bounded model checking. The tool that we will look at, the third tool and fourth tool that we will look at, they allow bounded model checking. So they allow you to explore everything in some region of interest. Not everywhere, because that's maybe impossible for the tool, or impossible in general, because there are some limitations of what computers can do. And then in the not bounded verification, but the real verification, there you can go even for checking all behaviors of the system, no matter how large. So yeah, we will look at those two things, and we will also look at tools that can basically check everything about the system. And yeah, of course, if we only check a few things, we have maybe low confidence, but if we check everything, we have high confidence. But it says here low human labor, because, well, you just write some tests. But if you want to really use this verification, there is a cost to it. So we're not going to apply verification to an everyday's website or mobile app. We're going to apply formal methods and verification usually only to some maybe safety critical systems, very important software systems. We will see some examples of where they are applied in industry. So if I say we're not going to use them for websites, that's not true. There are some companies that require that. But you also have some very critical infrastructure running on the web, right? So, and actually, there are some examples of tools from formal methods that made it into everyday development. So there's some stuff like null pointer analysis that you get some warnings here in your code. You might dereference a null pointer, or you might try to access a variable which is not initialized. This stuff actually also comes from formal methods. So this is stuff that now made it into just the regular tools that we use every day. Okay, so now if we have logic, what are we going to do with this logic? How are we going to use it for maybe learning something about our system? So here we have a very, very simple example. We have just an argument. So if the train arrives late and there are no taxis at the station, then John is late for his meeting. Then John is not late for his meeting. The train did arrive late. Therefore, there were taxis at the station. Is that correct? Who thinks it's correct? for a valid conclusion? Sorry? So if the train arrives late and there are no taxis at the station, then John is late for his meeting. So that's like, it doesn't mean that there are always no taxis, right? It just says in the case that the train arrives late and in the case that there are no taxis, then John is late for his meeting. So this is like a relation between those events, or yeah. So how would we try to solve this with logic? So first, when we use logic, we usually don't use like those long sentences. We try to use some maybe variables that might be true or false, right? So we're going to use one of the most simple logics. We're going to use propositional logic, right? So we have variables, they can be true or false, right? 1, 0, great. Hopefully we can handle this, right? So how do we write this in variables? How many variables do we need? What are the things that can independently be true and false? Okay. So let me try to try to write this down. Okay. Now, which way do I have to flip? This way looks good. And then maybe I can drag it. Oh. Okay, so what was it? The train arrives late? Okay, so that's basically the true and false, right? So if we say train late, I mean, we could say train on time, or we could say train late. Yeah, it's difficult to read like that, right? Yeah, okay, so let's say train late. This can be true or false, right? What else would we need? So what should we call the variable of, yeah, just taxis? Okay. Okay. John late? Okay. So the relation, okay, let's look at the variables first. Are there other variables? Other things that can be true or false in these sentences? So, well, can we capture everything now? And how do we now capture those things? So the first, well, let's look at this sentence here. Sentence number 2. How do we capture sentence number 2 with our new variables? Well, just this one. How do we encode this as a variable? We have a variable that says exactly this, right? This John late. So actually, if we want to write this down, sentence number 2. Sentence number 2 is just John late, right? Then 3. You need to see the variables again. Train late, right? That's easy again. Sentence number 3 is the train did arrive late, so that's simply our variable train late. So I mean, we just write train late, but that actually means train late equals true, right? But we don't have to write equals true, because if we just write it without negation, then it's true. Now the more tricky one is the first sentence. If the train arrives late and there are no taxis, then John is late for his meeting. So how do we write that? So train late. We also need something about the no taxis, right? But what's the relation between train late and no taxis? Sorry, taxi, right? Taxi. So we need to say no taxi, so we're just going to write the negation could write it like this, right? So there must be some, if both of them happen at once, right? So let's put an and between them. So train late and not taxi. Yeah. Yeah, I wanted to make this the negation. Second one. John late. John is not late. Yeah, true. There should be a negation as well. Yeah. Yeah, and then we still have this part. Then John is late for his meeting. So we need John late. Yeah. But how do we connect the first part and this part? An arrow, yeah, for implication. Yeah. So this basically is an implication. If this is true, this implies that that thing must be true, right? So yeah, we can formulate it like this. And now let's look at the last one that we want to actually see whether that's correct. So therefore, there were taxis at the station. So that's simply kind of, therefore, we probably need to see how to write that. But if we want to say there were taxis at the station, that's simply taxi, right? So, and that is like, yeah, maybe we shouldn't write it. This therefore, what does this therefore actually mean? It means taking all of these into account as being true, then also taxi is true. So it's basically a bit more complicated. So it's like 1, 2, and 3, they imply taxi, right? Okay, so now how do we check this in a logic? There are different ways. There are many different ways. Have you seen any way to do this? So if we have those variables, how many variables do we have? We only have 3 variables, right? Each variable can be true or false. We could actually check it exhaustively. Did anybody ever hear of a truth table? Yeah. So we could write down a truth table for all the variables, then check when all of these are satisfied, when all of these are true, whether also taxi is true. There are different ways. So another way would be by, well, maybe rewriting the constraints in a way that we can then automatically derive this constraint, right? This is a very different way. This is more like a symbolic way, whereas because we use these symbols and push them around to come up with something that says true, as compared to this more, well, exhaustive search way where we look at the truth table for all of these, and when all of these are true, then also that one must be true, right? So there are different ways to do that. So now let's look at, that's basically the same formulation, but not with nice variable names, just P, Q, and R, as many times in textbooks. Now, if we have a completely different argument, so here we have, if it is raining, Jane does not have her umbrella with her, then she will get wet. Then Jane is not wet, it is raining, therefore Jane has her umbrella with her. Completely different story, right? Can we solve it in this, or address it in the same way? We actually haven't solved it yet, but can we address it in the same way? We need to again identify what's true and what are the variables, what can be true and false. So we can again write a formulation in propositional logic. And actually, if you look closely, if P and not Q, then R. If P and not Q, then R. So this thing is the same, just Jane and John interchanged, and taxis and rain, and So actually, although it's very, very different conclusions, here we conclude that Jane has an umbrella with her. here we conclude that there were taxis at the station, right? Completely different worlds. We can still use the same logic to formulate this. And that's what these kind of formal methods are. You can solve all kinds of different problems if you just know how to extract the correct formulation out of the problem that you're trying to solve. And that's one of the main challenges. How do you know whether you can actually solve this problem with the formal method? Here, well, we can check, are there things that can be true or false? Is there some deduction step necessary? Is there some only logic connectives between the things that can be true and false? And then we can say, yeah, maybe we can solve this with propositional logic. There are other things that we might be able to solve with the same logic, but it would be much more complicated to solve them with that logic. And there are other things which then there's no way to solve them with this propositional logic. And we will also see those cases. So for example, if you have real numbers, it would be very, very difficult to formulate it with Booleans, right? Of course, in computer systems, we know we can kind of do some rounding and represent them using bits, so kind of Boolean variables, but this gets really, really tricky. And there are other tools. The second tool that we will look at that do much better with also real valued variables or strings, stuff like that, everything that is not really Boolean valued. Okay. Yeah, so that's some kind of motivation. These are actually the same argument. So if we have a tool to check whether this deduction step is correct, then we can also solve those different cases. So yeah, we can then, of course, not only do this to natural language text statements. If we can do this to programs, and we can conclude that the conclusion about the program, or that we can derive that the conclusion about the program is correct, then we could actually have a correct from construction program. Now, it's an open problem, and we know that this actually, the question, can this be solved for any program? Who has a computer science background? Okay. Can this be solved for any program? Can we have a computer that checks properties, even very simple properties, about any program in any programming language? Or maybe let's say any program in Python or any program in Java. Can we have a program, let's look at even a very, very simple property, that the program terminates. So is it possible to have a computer system that looks at a Java program and tells us, yes, this Java program is going to terminate? Or at a Python program or anything? Or at a Turing machine? Sorry? Yes, Turing machine is a concept for things that can be computed. So actually, if you can compute it on this computer, you can compute it on the Turing machine. So there's some equivalence between stuff that is computable and a very, very simple model of computable stuff is a Turing machine. And Alan Turing invented this. Who doesn't know what a Turing machine is? Okay, who knows what a Turing machine is? So it's a concept where you basically have an infinite tape. So you can't implement it because you don't have infinite tapes. And you have a head moving left and right on this tape. Or I think maybe can it stay in place? I don't know. But it can write stuff to this tape. Very simple symbols. It can write maybe a 1 or a 0. And it can move, I think, left or right. And that's probably all it needs to do. And this way you can simulate a computer. And it gets really, really complicated really, really quickly. But they are a theoretic model of stuff that can be computed. And if you can show that something is impossible to compute using a Turing machine, then you know that it is impossible to compute using any computer system. And that's actually what Alan Turing did. So he showed that there are some properties that are impossible to compute using any computer system. So many of the languages, programming languages, they have a property called Turing completeness. And basically, if a language is Turing complete, then we know that it is complicated enough so that we are unable to figure out whether it terminates or all other kind of interesting problems. So all the programming languages that we have, or most of the programming languages that we have right now, they are Turing complete, and basically there's no way to prove that they even terminate. So what does that mean for formal methods? It means they have limits. So there's no way they can solve all the problems in the world. So people have been working to find clever ways around these problems. And that's what most formal methods do. They either find an abstraction of the problem that reduces it to the relevant aspects. So we made extremely strong abstractions here, right? There's Jane, that's a real person. There's, well, an umbrella. It might have a color. It might have different features, right? We don't know. Is it short? Does it fit in a purse? Is it a long one that you have to use as a walking stick? And we just said, well, this umbrella, that's a Boolean variable Q. So we made a huge abstraction because all we are interested in is from these facts, can we derive that Q is true, right? We didn't really care about the color or size of the umbrella. So that's what people do in formal methods also. We do abstractions of the complex programs, of the complex systems. There are things we don't need to consider to make a particular proof about the behavior of our system. So we will abstract them away, and we will focus on the stuff that we need to write our proof. So yeah. So although it's impossible in general, there are many ways that we can still address this problem. Yeah. So yeah, and even in addition, even if the logic would be possible, we might still have, I don't know, maybe bugs in our code or bugs in our implementation or even in the operating system, right? If we prove that our program behaves correctly whatsoever, if the operating system fails, then our program is doomed anyways, right? So, or maybe even the environment, if our computer system, we prove that the operating system is fine, that the program is fine, but then the house burns down where the computer is standing, right? So, yeah, there are always some kind of boundaries, and we need to set these boundaries. We need to be aware of these boundaries, and we then need to formulate these boundaries and take them into consideration into the analysis that we do. Yeah, so usually the main terms that we use are specification, which tells us what the system must do, these kind of properties that we want to show about the system. Then the verification, where we actually check the system against the specification. Does it really do what we want it to do? And then synthesis, this is another area. So there we're taking the specification and we say, well, give me a system that satisfies this specification. So this is where we don't even have to code, where the synthesizer will try to come up with a program that satisfies the specification. And all of these are, yeah, still very, very active research areas. Yeah, some specification in some language that we will look at. That's basically the third language that we look at. So before Christmas, still, where we might just specify linked lists and data that they have. And then we can check whether our implementation or our abstraction of linked list actually is correct. So here, maybe we want to know whether the reversal procedure of the list is correct. So if you reverse the list, is that actually a correct implementation? This is, yeah, probably some Java code written, so we need to abstract this into our formal modeling language, and then we can maybe check whether this procedure is correct. So we're just going to skip this because, yeah, you can read this code, but we will look more deeply into how can we formalize this in a formal modeling system, and then, yeah, maybe one thing that we should do in the last 10 minutes that we have is to look a bit who is using actually formal methods tools. Many people test, right? Many parts of industry test, but not everybody uses those formal methods. Often listed drawbacks are there's a huge learning curve. So you will see, I mean, we're handling 4 tools in this lecture, which has 6 credits. So hopefully you will master most of these tools, but there's a lot more tools. So it takes some time to know how to use these things. And not only knowing how to use the tools doesn't allow you to necessarily use them correctly and apply them to the problem that you have in the industry. So there's a huge learning curve. That's why I think usually those people that do know formal methods, they are quite well paid if they find a job in this area. And then we will see some companies that use formal methods. And yeah, it's usually hard to know if you specify the property correctly. So this, for our example with the train and the taxis, it's probably easy to see, yeah, this line corresponds to that line, but often there's not this easy one-to-one correspondence, and complex systems usually tend to have also very complex specifications. So then that's also difficult. And another thing that computationally intensive to run these formal methods. So there are some heuristics to speed things up, but some systems are simply impossible to really compute whether the specification is satisfied, or at least it takes a very, very long time. Yeah, now a quick question. Do they use formal methods? And that's again the same website. So I need to lock this question and publish. This was about the prime numbers. Okay, so I'm going to publish this question. So let's have a look. These are very different organizations, right? And which ones of them might use formal methods? NASA, Facebook, Amazon, Microsoft, or Rolls-Royce? Let's look a little bit at the statistics. Let's show numbers. Wait. Okay. Okay, so none of them are really clear winners, right? I mean, the highest is here at a quarter. So, and that's NASA. So, well, if you remember the first definition of formal methods, this was from NASA. Yeah, so they're basically the ones who started it, and they use formal methods. Why would NASA use formal methods? What kind of code do they have to write? For space rockets and satellites and all this kind of stuff, you don't want that code to fail, right? So it will be really, really expensive if that code fails. So yeah, they use formal methods. Facebook has the lowest. So let's maybe go in order. Rolls-Royce. What does Rolls-Royce build? Cars and engines, yeah. So they also build the jet engines for planes, right? And you also don't want those things to fail. Yes, so Rolls-Royce also uses formal methods. Yeah, and when I was in the UK, I was at the University of Leicester. We had some students that actually worked with Rolls-Royce, and they were using formal methods in their internships. Okay, next one, Amazon. What does Amazon do? Sell books, right? Sorry?
Huge equipment for this sorting warehouses.
Okay, for the warehouses, yeah, but they actually do much, much more important stuff than their warehouses and their selling, yeah? Payments, yeah, but what? Cloud services, exactly. They have these Amazon Web Services which run, I don't know, a quarter of the internet or something, right? Because they have virtual machines where tons of companies deploy their software. So if Amazon Web Services goes down, most of the internet as you know it is gone. So there were some cases a few years ago where they had some configuration that somebody misconfigured at Amazon Web Services, and then all kinds of websites that you wouldn't even think have any connection to Amazon Web Services, they were not available. So all kinds of maybe booking companies and everything, they were suddenly not available. So Amazon Web Services is really an extremely popular case for using formal methods. Then let's get to the lower end, 18% for Microsoft. Well, Microsoft does Word, Excel, Windows stuff, right? Do they use formal methods? Probably. For what? Okay, yeah, they also have their cloud computing platform, yeah. So very similar to Amazon, they probably also do it, yeah, but also maybe even just on the local machines. So operating systems. You don't want those to fail. And you there's one, I think one of the early examples where they used formal methods was the verification of device drivers, because they operate on a very, very high level, and they can do almost anything to your machine. So you want to verify that they work correctly. So Microsoft is also, there is this Microsoft Research. There's the regular Microsoft that does the Word and Excel stuff. And Microsoft Research, they actually do all kinds of research in different areas, also in AI, of course, but also in general software engineering. So they have different labs in the US and also in the UK, Cambridge. They have Microsoft Research, and they do lots of stuff. And one of the tools, the second tool that we will use, it's actually developed by Microsoft Research and now open source. And yeah, so Microsoft also does formal methods. Last one, Facebook. What does Facebook do? Who thinks they use formal methods? Well, 15% of you. Well, not 50, 15% of 12 people, right? Why would Amazon use formal methods? Sorry, yeah, Facebook, sorry, Facebook. To steal your personal data? No, but actually, I mean, one reason why they do it is they have, well, a very popular social network, which has tons of different client applications. And you don't want those to fail. You don't want them to, I don't know, not work on iPhones, but only on Android phones, or not work on older Android phones, or crash. So Facebook is also a very, very popular, has a very, very popular research unit that does a lot of formal methods. They need to develop software. They need to develop software fast. They need to ship it to millions or billions of customers, right? If your software runs on millions or billions of devices, you don't want it to crash. And if you want to compete with others in the market, you need to release fast. And for that, you need to ensure that you have good quality, and just testing will not do it. So the answer is all of these use formal methods. But yeah, these are also really big companies, right? Okay, so yeah, traditionally, of course, with NASA, it's safety critical systems. You want the space rockets, the satellites, everything. You don't want them to crash. Then they had a formal methods research program at NASA Langley for safety critical avionics systems. Also, you can imagine that in the avionics industry, you also don't want the software in the plane to stop and say, please reboot, right? That's not a good idea. Other high assurance computer systems. Then recently, there's more automated reasoning. It's not only about safety critical. The question is, well, what is really safety critical? But we see that these companies, which you would not usually associate with safety critical, because maybe lives do not directly depend on whether you can browse your Facebook or not, right? But still, those are really big players in formal methods now. And one of the softwares that they released, so of course now depending on the company and what is the focus of the company, they might work on very different aspects. So one of the tools that Facebook research is very famous for, this is this Infer tool. It's a static analyzer that can analyze all kinds of issues in code. So like the stuff that you have in your IDE that tells you that you might have a memory leak because you forgot to close a resource, or that you might dereference some null pointer, stuff like that. That's all based on static analysis. And one of the, well, early engines, well, it's 2015, that does that in a large scale for a huge code base, that this Infer static analyzer that was actually developed at Facebook. Then at Microsoft, they are quite popular for this Z3 SMT solver, which we will use as the second tool. Then also Daphne verifier. That's also some, I think, .NET language, or integrated with multiple of the .NET languages, where you can specify some behavior of the code and prove it. So that's a lot more, let's say, manual work than this Infer tool from Facebook. The Infer tool from Facebook is really for the average developer. It gives the average developer some hints about, here you did something wrong in your code. This Daphne verifier is more for the really more critical systems, where the developer has to say, I think my code is correct, and this is how I'm going to prove it, by doing some annotations in the code. And then some very, now historic examples, basically this device driver verification, because device drivers, when they crashed, you always had these blue screens, or reboots, at least in Windows. And then they started very early with formal methods on this. So that's, almost something like 20 years ago. They did device driver verification because that was one of the pressing issues back then. And they have different now also for program synthesis, so not only verification, but also synthesis. And actually, did anybody ever use Excel, Microsoft Excel? Yeah. And did you ever drag down some complex, numbers that you wanted to be replicated, the computations to be replicated for different cells? And have you come across more complex examples where you can do string manipulations? And there's a tool called FlashFill. So if you have more, let's say, I don't know, you have a list of people with first name, last name, and I don't know, other information, and then you combine this to more complex string concatenations, you can also do this kind of dragging it down, and they will actually try to come up with a program that replicates the behavior that you did manually. So they will come up with scripts. There can be a few lines of code that actually replicate this. So that's program synthesis, because from a few examples, they try to guess how you want to complete this. And that's, for not even for the average developer anymore. That's like for the average user, right? So stuff like that, that's also formal methods. I think there are a few more examples, but we are out of time for today, so we're going to continue them in the next session. And the next session should be on Friday, I think, right? Yeah, so next session that is on the schedule. This will be, again, a lecture. So we will continue with this material and start the first tool and language. Okay, see you then.